Hello everyone. We are going to start the new topic. We are still on the topic of terpenoids and we are going to do structure elucidation of alpha terpineol and its synthesis. As we told previously, this natural product studies was of great importance because that's how organic chemistry developed. So this was one of the molecules they had found initially and then they tried to discover what is it and how does it look, and we are going to look at it. Okay. So this alpha terpineol, when they initially saw, what they saw is it was optically active. And it was found in both plus and minus, that means dextrorotatory and levorotatory. And see, chemically it will give all the same reactions. Only thing, optical activity will be differing. Otherwise, all the physical chemical properties will be same. Okay. So for a long time, they wouldn't have realized that there are two different molecules. Unless you put in biological system, unless you put them in biological system, you cannot make out that they are different. Okay. So this plus form or the dextrorotatory form is found in the oils of petitgrain or neroli, and negative form or levorotatory are found in camphor oils, right? Now alpha terpineol, either of them, they are used in perfumes. Okay, right. So this is the structure of alpha terpineol. If you see, it's a cyclohexene with a methyl group on top. Down is tertiary alcohol group is there, and here this is the hydrogen. Now this is the chiral center. You can see here substituent is different, here substituent is different, here it's different, here it's different. So 4 different substituents are there, and so now this H can be towards the viewer or away from the viewer. So these both will be enantiomers, and that's how it is, alpha and beta. Okay, so let's start with the structure elucidation. The structure elucidation, the molecular formula was found to be C10H18O. I said there were instruments previously also, you can find out what's the thing. Then degree of unsaturation, there is a formula which we will deal later, but simple things you can understand here. When it is group 16, that is oxygen, sulfur and all, we don't need to worry. We have to just think as alkane and then see how many hydrogens are less. So it is C10. So for alkane, the formula is CnH2n plus 2. So it will be C10. So H should be 2n plus 2. So 2 into 10 plus 2, that is 22. But here it is 18. So 22 minus 18, that is 4 divided by 2. So degree of unsaturation is 2. Okay. Now they have to find out what are those two. Is it 2 double bond or it is cyclic, or what kind of that unsaturation is. So what they did is they reacted with bromine and they got dibromo derivative. So one thing is very clear, if dibromo derivative is forming on reaction with simple bromine, that means alkene is present, simple double bond is present. Okay, so one double bond was confirmed. Now other we don't know what is the second double bond. It can be aldehyde ketone, that also forms, gives you another degree of unsaturation, or if it is cyclic, it will give you another degree of unsaturation. We know degree of unsaturation is 2. So this is what they formed. They reacted with the bromine, as you see, it got added, not substituted. Everything was remained same, plus 2 extra bromine got added. Okay. Now the search was to find out the nature of oxygen. So nature of oxygen, of course, we talked about yesterday. If they give positive test for 2,4-DNP, we know it is carbonyl. There's another thing. If OH is there, no, you start reacting with steric ammonium nitrate. Okay, so they would have done a lot of things. It's not the directly first thing they did this, but what gave positive test to for them was steric ammonium nitrate. So when they put steric ammonium nitrate, it gave red color. Okay, so when it gives red color, it says that this OH, there is OH group, and the OH is alcoholic in nature. What I mean to say is not phenolic. But phenolic is there different test. Actually, you get a purple color when you use FeCl3 solution. Okay, alcoholic FeCl3 solution. If you add, if you aqueous FeCl3 solution when you spray, if it is phenolic, it will show you violet color. But if it gives red color with steric ammonium nitrate, that means alcoholic OH is there, and this is how they confirmed it is alcoholic OH. Okay, and then so one thing is clear, it is having OH group. Now they want to know it is primary, secondary or tertiary. So when they reacted with acetate group, it's a very, very simple reaction. It never fails. Put acetic anhydride in pyridine. They saw that reaction was not happening. And that can only happen for tertiary. Even if it is secondary, it's very, very easy reaction. I have done 100 times. Just put at night and go morning you come, this reaction will happen. There's no way you can miss this product. But if it was not happening, that means it is tertiary alcohol. They reacted with the acetic anhydride and pyridine. You know acetic anhydride, maybe I'll write it for you, you will understand. Acetic anhydride, acetic acid, 2 acetic acid, loss of water, O, C double bond O, CH3, okay. So this oxygen goes and attacks, and this will go up, this will come down, and this leaves. That's how acetate should form. But because it is tertiary, too bulky, it is not allowing oxygen to go and attack. Therefore, they confirmed the alcohol is tertiary. Now, nature of terpenoid. So they want to know it is cyclic and non-cyclic, what it is. Now, since the degree of unsaturation is 2, 1 they found it is double bond. Now they also saw it is neither carboxylic acid nor, because only one oxygen was there, if you remember. The formula was C10H18O. So it cannot be carboxylic acid anyway. It can be carbonyl, which they didn't find. They found that it was alcohol. So the only way to show that the another degree of unsaturation is because of ring. So one thing is very clear, it is having a ring, that too monocyclic. If it was bicyclic, then there should have been higher degree of unsaturation. But because there is only one more degree of unsaturation, so it is monocyclic terpenoid. Then what they saw is, like yesterday they had used some other dehydrating agent. Here they reacted with concentrated sulfuric acid. So concentrated sulfuric acid, you should know, it's a very, very, very powerful dehydrating agent. So again, like yesterday's molecule, here also it gave pyrazimine. So one thing is that when you get this molecule, you know what is the skeleton. So skeleton was like this. That's what they came to know. Now, what all things till now they know? They know the skeleton is like this. They know it is cyclic, so anyway it is cyclic. They know one double bond is there because one bromine got added. And they know one alcohol is there. And that too, alcohol is what? Alcohol is tertiary. So alcohol can be a lot of places. Alcohol can be, OH can be here, OH can be here, OH can be here. But it cannot be here, here, here and here, because if OH was here, they would have been secondary alcohol. Okay. Now they want to know the position of double bond. Now double bond can be also anywhere, here, 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 here. A lot of places are there. So they did all these reactions. See, just to read, understand, mug and write exam, it is so tough. Imagine they do all this work in lab and pull up little by little ideas, the results, and then they try to find out. Now we don't need, now it's so very simple to do all this. You do a simple NMR, you'll get a lot of ideas, you'll know exactly what is the structure. Before there was no NMR, and that was the biggest pain. So they had to do a lot of these things, okay. So they took this alpha terpineol, spelling remember, okay, terpineol, NEOL, terpine, all is alcohol, INE is there because it is having alkene, okay. So they reacted with 1% alkaline KMnO4. You know, if you react with 1% alkaline KMnO4, you have studied, the double bond breaks up and gives you 2 OH group. So what molecule was found to be having is trihydroxyl compound. So one thing is very clear, one OH was already there and a double bond is there which has broken up and has given you 2 more OH groups. So that's why the compound was trihydroxyl. So all these are very simple chemical reactions. You can find out exactly how many moles has reacted. So you'll know that it was 3 OH has been formed, okay. And then they reacted, they oxidized with chromium oxide and ACOH. It's pretty much like chromic acid. And they got ketohydroxy acid, which further reacted. This was a transition, it was intermediate, which they might not have been able to isolate, but must have given some kind of spectral evidence, okay. And then this this trihydroxy compound on oxidation gave gamma ketolactone, okay, and the formula was C10H16O3, and then that broke up and gave acetic acid and this C8H12O4, terphenolic acid, which on oxidation with KMnO4 gives terebic acid, okay, C7H10O4. Now, of course, I understand it makes no sense right now, but we'll try to understand what all things have happened. So first step, if you remember, first step what they did is they added 1% alkaline KMnO4 and it gave you trihydroxy compound. So what does it mean? The formation of trihydroxy compound with this thing due to hydroxylation olefinic bond present in the compound. So that's very clear, the double bond is there. So that has broken up and it gave you 2 OH group and 1 OH was previously there. Right. Now that OH, when they further oxidized with chromium trioxide and acetic acid, it gave keto-lactone, that is 4. Okay, that is 4. After it came here, it gave this gamma keto lactone, right? Where am I? Right. Now this formation of gamma ketolactone stone is due to breaking of vicinal diol bond present in the compound 4, and without loss of any carbon showed that double bond is present in para-methane ring of compound 1. What I am trying to say is, if you see the number of carbons, okay, here it was C10, still it is C10, oxidation still gave C10. Now you have oxidized it. Sorry, yeah, initially you broke, you formed OH, then you're oxidizing it. So chromic acid, if there is a OH outside, like 2 OH are on carbon on acyclic system, if something like double bond O is there. So this something like here double bond is there, okay, something like this double bond is there. You react with alkaline KMnO4, you get OH here, you get OH here, and then it breaks up. So if it breaks up, the number of carbon becomes less. But here the whole molecule carbon did not become less. So what does it mean? So first thing was very clear, there is already OH group in the molecule. They reacted with alkaline KMnO4, they gave 2 OH. This one is very clear, everybody is very clear, okay. Let's see ahead. Now they reacted with chromic acid. So as I just now showed you, here also if you react with chromic acid, it basically breaks up. And when it breaks, if something is giving you acid, so something is giving you acid, we have seen that it the intermediate was ketohydroxy acid. So carboxylic acid is there. So that means here one hydrogen was there at least, because that only will oxidize initially to become aldehyde. Aldehyde will further oxidize to become acid. But here there cannot be hydrogen, it has to have at least 2 alkyl group, okay. If 2 alkyl groups are there, then only when you oxidize it will become ketone, and ketone cannot be further oxidized to carboxylic acid. And what they saw, it gave you gamma acetolactone. What is lactone? Lactone is nothing but cyclic ester. So one OH is already there, okay. That OH reacted with this COH, and you know this simple reaction is there, we have done a lot of times. Alcohol reacts with acid in presence of strong acid. Alcohol with carboxylic acid in presence of strong acid forms you ester, and that's how they got cyclic ester and a ketonic group, okay. Now ketonic group, they want to find out what kind of ketone it is, okay. So one thing is there, the ketonic group and lactone group was also confirmed by IR spectra. So IR spectra we'll study later. IR spectra is one of the spectra which tells you only and only functional group. It doesn't tell you anything more, but very clearly to tell you which kind of functional group is there, okay. And then what happened? And they did iodoform test on it. Now iodoform we have studied again, okay. Iodoform only when you have been having CS3 C double bond O, or you are having something like CS3 COH. These kind of structures, they give positive test for iodoform. So here also it gave positive test for iodoform. So very clearly they said that there is a ketonic group, and ketonic group, this CS3, because it later lactonized. So you think about lactonized product, so we are not touching that part. So only the ketonic group will give. So it gave iodoform test positive. So positive is this, you get iodoform, very nice yellow color it spreads out, okay. So they saw iodoform. So one thing was very clear, what was there besides C double bond O was CH3. So partial structure, what they know till now is they had got this skeleton structure, okay, and then one clear cut double bond is there. So that's what, if it breaks, what we'll get is this will become aldehyde, further oxidized to COOH. So it has to have hydrogen, and this part they said it cannot be hydrogen, both R should be there. One R has to be part of cycle, okay. Please think about it. It's a little bit, if you think you'll get it, okay. And another part they knew it is CH3 because it gave positive test. Now this part was clear because they know the skeletal ring, this parasamine structure was isolated, and they realized that part, okay. Now two things are there. Now it is chiral, so this OH can be here, OH can be here. So I think they did not touch much, but did not think about optical activity that time. Otherwise, very clearly OH cannot be here because this molecule is chiral. So if it is chiral, these two are it cannot be chiral if OH is here because these two R groups are same. So very clearly this OH should have been here, okay. And then this compound 5, what was the compound 5? Compound 5 was acetic acid and this compound. So acetic acid broke up, and what they saw is this structure was found. Where is it? This structure was found, okay. So if this structure is there, so ketone group is there, that means this OH, you understand, this OH is part of this has broken up and this is formed. So this OH is from this part of the ring, okay. So very clearly they understood that this OH has come from this part of the ring, and that's how the structure of alpha terpineol was confirmed to be this one, okay. Now the rest is synthesis. They did a very simple reaction. Such a complex molecule, very easily they formed it. They took this molecule, okay, it is butadiene, 2-methyl butadiene, and there is a dienophylline group. So it is CH2 CH COOCH3. So we'll study about this. A very detailed complete chapter is there. What is called as pericyclic reaction. The simplest pericyclic reaction is this Diels-Alder reaction, or 4+2. What I mean by 4 is 1 2 3 4 pi electrons are there, and 4+2, they in presence of heat, they react, and that's how they reacted, and you're getting this product, okay. So they reacted with this. You have to mark this. So this double bond comes here, this double bond moves here, this double bond comes here, and you can see the mechanism. Very, very simple. So this pi bond has come here, formed a single bond. So this pi bond disappeared, formed a single bond. This pi bond moved up, so it has moved up here, and this pi bond is attacked here, so this bond comes here, okay. And then they reacted with CH3 MgBr. Excess means twice it will react. So it is very clear, very simple. So first CH3 will go attack here, so that it will become O minus, comes back again, this OCH3 goes. Then again one more CH3 will go and attack here, so we are getting 2 OCH3 and OH. That's what we are getting, 2 CH3s and OH. So we are getting this mixture of alpha terpineol, okay. If you have mechanism, maybe I'll do it once again, but this is very simple mechanism, we have done 100 times. Let me do it once again, okay. CH3 MgBr. So you know Mg gets positive, carbon gets negative because metal is electropositive. So this goes and attacks here, this comes here, and this comes back again, and this leaves, okay. So what you get is this one. You're getting C double bond O, and you're getting CH3. And second step again, CH3 MgBr is there. This negative goes, attacks here. You get this one. Sorry, you get this one, OMgBr, CH3 and CH3. Once you hydrolyze it, you put H3O plus, or just water you put, still you'll get that, okay. And you get this COH CH3 CH3, okay. Thank you.